And if he has a company, you will
All right, good morning, everyone. Today, we're just going to be practicing with this method that we learned yesterday. So having to know how to adapt between orientation of our methods, whether it's top minus bottom or right minus left, that is what I want us to be able to get comfortable with today. And if we can get comfortable with that, that's going to give us that foundation that we need for tomorrow when we look at washer method, where the formula is a little bit more complicated, but the concept is the same. So if we can do well today, tomorrow will just feel like a natural progression, and we're just kind of just building on top of what we are going to do today. So. Okay, we'll do some practice problems today. Tomorrow we'll do washer method, which is basically where there's a gap between the shader region and the axis, and because of that gap, we have to subtract out a hole so that we can find the true volume of the object. So that's really the only. So we're basically just going to be extending this method for this scenario where there's a gap or a hole in our object. Okay, Friday we'll try to put things together. We're kind of mix some this method and washer method and see if you guys can recognize it and apply the appropriate formula. Monday we still have one more thing to do with cross section. These objects are going to be strange looking, but we don't have to draw the graphs. We just have to be able to recognize what we need to pull from it, and a lot of what we're going to our foundational work is going to be all here, and then we're going to do a little bit of adaptation with different formulas, but hopefully we won't find that difficult. We're just kind of adding on top of what we already know. Tuesday, Wednesday, we'll do test review, and then Thursday we'll have our test right before we go on, or you guys go on break. Okay. Any questions? All right. Let's look at our this method worksheet. You guys picked it up from, you guys should have it in front of you or at home. The link is under today. Okay. All right. Does everybody have one? So let me go through the two methods here. The two methods that we're using is top minus bottom and right minus left. So top minus bottom is the one that we all probably just feel more comfortable with because everything is already given to us. There's no need to make any messy adjustments. But a visual reminder as to when to use top minus bottom is when you draw your radius is sitting as a vertical radius. So if you see a vertical radius, you know that it's a visual reminder that you're going to be using this formula, this method for top minus bottom, okay, where your bounds are in terms of x, and then your equations are all going to be comfortably as a function that we recognize, right? We're used to seeing y equals, and this is going to be the more the format that is just more recognizable to us, more familiar. Now, if our radius ends up being horizontal, then we have to make quite a few adjustments. Okay. So understandably, this is the format that students struggle with, just because there's just more things you got to change. You got to change the way you look at the bounds. The bounds are no longer in terms of x, they're in terms of y. The equations have to change as well, and that's an additional step that a lot of students either forget about or don't realize. So we have to be able to make sure that our forms are proper And that a lot of times requires us to rewrite the equation that's given to us at the beginning. Okay, so we'll explore both types as we look at these problems. Number one, let the region R be the area enclosed by the function y equals 2x cubed. So here's y equals 2x cubed. The horizontal line y equals 8 and the y-axis. Okay, so we have our enclosed shaded region here. Find the volume of the solid generated when the shaded region is, so part A, rotated about the line y equals 8. So anytime you see the word rotation, you know that's referring to your axis of revolution. So I know that my axis of revolution is at y equals 8. Okay. I would like for you guys to use dotted line for your axis of revolution. That way it's a nice reminder where to begin drawing your radius, and also where the center of your object is. I know that is not what you see in front of you. It doesn't look like it's the center. It looks like it's the outer edges of your region of what you have in front of you. But notice that we're going to be rotating this, right? So when this gets rotated, when everything's said and done, this is going to be the center, and we're going to have this bowl-shaped object, and there's going to be a portion that's going to be sitting up here as well, right? So the reason why I want us to keep reminding us that we're looking at the center is because this is how that's why we start to build our radius from that point, right? We have to remember when you think about radius, you're always thinking about the distance from the center of the circle to the outer edges. So technically, this is the center of our object, and we're moving to the outer edges of our shaded region, which is the outer edges of our bowl or object. Okay, so also your radius is always going to be perpendicular to your axis of revolution. So we see a horizontal axis, we should be expecting a vertical radius. Okay, so we're going to start building our habit of drawing our radius in a way that will prevent mistakes, especially tomorrow when we look at something that may cause us to make mistakes. Always start on your dotted line. If you always start on a dotted line when you build your radius, you will avoid the mistake that we're going to see tomorrow. But today, we're just practicing that form. So put your pen or pencil on the axis, and we're going to extend to the boundary of the shaded region. Okay, we see a vertical radius. Normally, we know that's going to be potentially an easier problem because there's going to be less adjustments needed to get it ready for our volume formula. So we're going to start building our radius expression. Okay, what's the top of the radius sitting on? Y equals 8. So we know that the top function is going to be 8. Let's look at the bottom of the radius. What's the bottom of the radius touching?
2x cubed.
Yep, y equals 2x cubed. Okay, so we identified everything that we need to build our radius. So we're going to start putting our, let's just find our radius, and then we can worry about the formula later. Okay, top minus bottom. The top of the radius is sitting at 8, so that comes first. We always do top minus bottom. I like to put parentheses around the bottom function. I think that's a good thing for us to do. And if we realize that we don't need the parentheses, we can always drop it later. But this is a reminder where if there were multiple terms that we're going to be reminded, oh, I may need to distribute that negative through. In this case, not going to be an issue, but we may see something that requires that parentheses. So if we always put it there, then we're always reminded to look for any potential distribution that needs to occur. Okay, now we have our radius, but we still need what? What else do we need for our formula? Yeah, we need the bounds. Okay, now think about what these rectangles look like. This is one representative rectangle, but all the rectangles are going to be oriented like this. It's always going to be vertical. So imagine all these vertical rectangles to the left and to the right. Now, how far left are these rectangles going to extend to? What's the left bound of our shaded region? 0. Yeah, y-axis, which is going to be x equals 0. So we know that's going to be perfectly perfect placement of our x1. That's going to be our lower bound. Okay, how far right are these vertical rectangles going to extend?
All the way to the 2x cubed.
Yeah, all the way to this intersection, right? And if you look at that intersection, looks like we can kind of estimate where it is. Maybe it's 1.5, maybe it's a little bit more. But how can we get a more accurate read to that of that intersection? Yeah, we're going to set the two equations equal to each other. Okay, good. So find intersection. So intersection of the curve with the horizontal line. So we'll say 2x cubed is equal to 8. Algebraically, we just have to move things around to eventually get x by itself. So let's divide both sides by 2. X cubed equals 4. And then take the what of both sides? Cube root, okay? Now, it's not going to come out to be a nice number, right? So you can either hold on to cube root of 4 as your upper bound, or sorry, as the bound on the right, or you can get a decimal value out of it. That's fine as well. So let me show you. If you want to enter that in the calculator, cube root, there's a shortcut button there. If you do math, there's an option for cube root right there, math 4. So if you do math 4, cube root of 4 gives you 1.587. You can use cube root of 4 for upper bound, or you can use 1.587. Okay, so maybe cube root of 4 because it's more accurate, but I think it's close enough. It's not going to change our answer. If you want to use, if you want to find cube root of 4 on your 36 Pro, you're going to have to use the box radical there. But we need to first identify our roots. So you have to type in 3 first, and then you see that second box root there, second x with in the blue here. So if you do second, then it's going to push that 3 up into the root position, and then for same answer, 1.587. Okay, so we have our intersection here. Okay. All right, I think we have everything we need to create our volume equation. So let's do that. V equals pi integral. We're just going to follow the formula piece by piece here. So x1 and x2, we want to look for left to right. We said 0 to 1.587. Okay. We have to square the entire radius expression. So if you want to drop the parentheses, that's fine. We know that there's no multiple terms we got to distribute, but we do need to square the entire 8 minus 2x cubed. So I want to put a bracket there just to make it more visual, but in your calculator, it'll be parentheses. Okay, any questions here? Oh, wait, let me back up. There are other ways that you can find that intersection. Okay. So if you want to, you can use numsolve on your 36 Pro. Let me show you. Now, I think this is easy enough we can do by hand, but if it gets more complicated, I want to make sure that you guys know about this feature here. So numsolve is under, if you do second sign will take you to numsolve. And just type in 2x cubed equals 8. Hit enter. I like to start at 0. Enter again. Okay, 1.587. Okay, same result. On the graphing calculator, there's also something similar to numsolve. If you do math, and it's the last option, but if you go up, it's going to go to the bottom of the list. So if you go math and then go to that'll take you to the very bottom of the list. There's a solver. And you can type in an equation set equal to 0 and then look for the intersection. So if you do 8 minus 2x cubed, then it's going to find that intersection for you, 1.587. So math, hit the up arrow button, it'll take you to the very bottom of the list. I mean, so you can scroll all the way down, but if you hit the up arrow, it will go to the bottom. So that's another option. Another option, you can graph the functions. You can graph the 8 and the 2x cubed, and then look for the intersection of those two graphs. So if you do second trace intersect, so second trace intersect, you can just ask the calculator to find the intersection of those two graphs. So first curve, pick a point relatively close to the intersection, hit enter. It's going to ask you for a second curve, so the cursor should be on the other graph already, but I like to just kind of move it a little further away from the axis, from the intersection, so it doesn't get confused. I want it to be close, but not on the intersection. Doesn't matter which side you're on. Hit enter again, and now it's going to ask, are you ready for me to guess that approximation? Hit enter a third time, and find that same value, 1.587. Okay, a lot of options, but just want to make sure that you guys, whichever method that you're using, whichever calculator you're using, that you're comfortable if the expression ends up where you have to use your calculator. All right, so our volume equation, put into our calculator, math 9. Okay, parentheses first, 8 minus 2x cubed, close parentheses, and then I'm going to square my binomial. Don't forget the x at the end. Okay, volume equals 65 point, oh, let's see, will this convert to a fraction? Okay, looks like it does. That's a pretty messy one right there. I think the 36 Pro may not quite get us there. So I think in this case, you have two options. You can either write it as a fraction or as a decimal, because this is really messy fraction here. And we don't want to forget about what? What's also part of our answer? Pi, yeah, pi. Okay, so 3 decimal places, or if you want to write it as this one large fraction, you can. And then units cubed. Okay, anybody have any trouble with calculator? Everybody comfortable with entering everything in? It's good that you're practicing with the calculator next to you, just because there's going to be some potential unforeseen issue that you're not going to discover if you don't consistently practice with the calculator next to you. Just the placement of parentheses, placement of exponent, and errors that you're not expecting, right? You want to get comfortable with the keystrokes. I do want to point something out here. Some students have an older version of the graphing calculator, like a TI-83, and you may come across where if you hit math 9, it doesn't cleanly show you this integral notation, this math print. So if that's the case, you're going to see FN integral or FN INT. If you see that, it's basically the integral notation, but you're going to have to put it into this particular syntax. So you're going to put the expression, it's going to be the first thing that's going to be placed. So in this case, you'll put the parentheses 8 minus 2x cubed quantity squared, comma, followed by the x. So x is basically the dx that we've been doing at the end of our process, comma, lower bound. In this case, you'll put 0, and then comma, upper bound, which is 1.587. Right, so a little bit more cumbersome, but it does the same thing. It's just with the older calculator, you may not have that nice math print that matches what we see in front of us. Okay. All right, any questions with part A? All right, let's look at part B. Okay, rotate it about the y-axis. What's uniquely different about part B?
It's just rotated around the y-axis instead of y.
And the orientation is going to be different, right? Because now our axis of revolution is a vertical line, which is going to shift everything. We're going to have to rely on potentially a different form for this method. Okay, let's go ahead and draw our dotted line, axis of revolution. Okay, so we have a vertical axis, which means that we're expecting our radius to be perpendicular. We expect it to be horizontal. So this is the center of your object. We're going to be thinking of it as rotating this way here. So put your pen or pencil directly on the axis. On the dotted line. That's where you're going to start. And then we're going to extend to the boundary of our shaded region. So we're going to extend to the right. Now, if you look, this is a little different. Horizontal radius, which means we need a different equation, which means that usually this requires a little bit more effort to set things up. Okay, it's not going to be as quick and easy as what we like to do with top minus bottom. Now, the equations have to be in the proper form, which a lot of times is not. So we have to get it into this x equals form. Okay, so we know the curve has to be adjusted. We know the equation f of x, you can think of f of x as your y value, so y equals 2x cubed. All right, so what would your first step be to move towards getting to the proper form? Okay, so we're going to start moving things away from that x, right? So divide both sides by 2. Okay, x is by itself. What can we do now? Take the cube root. That will isolate x. So I have x equals cube root of y over 2. And this is now the proper form that is fit for eventually putting into our radius expression. So I'm going to point to what that's referring to. Okay. What's the left end point of the radius hitting?
Y for x equals 0.
Good, x equals 0. So look at the form. They are perfectly set up for what we need for our radius expression. See that x equals? Okay. They're taking on the proper form that we're going to need. Okay, let's build our radius. But now different notation here, r of y, not r of x. Okay, right minus left. What's the right endpoint of the radius hitting?
Cube root of y minus y over.
Good, y over 2, cube root y over 2. Right minus left, left is at the 0. Looks like that 0 is not going to have an impact. We can make it drop. And let's go to our volume formula here. Okay, v equals pi integral. Okay, different orientation, right? Vertical rectangles, we're stacking from the left x value to the right x value, so from 0 to 1.587. We're no longer going to be able to use those boundaries for our for this version of the formula, right? If you look, now we need y values. So we're stacking these disks a little differently. We're stacking it above and below. So they're all going to be stacked in this orientation. So we're going to stack all the way from the very bottom to the very top. And what's the lowest y value of the shaded region that you see? 0, okay. And what's the highest y value? 8. So sometimes we can just pull this by looking at the graph. It just depends on what the graph looks like. Other times, it may require more work where, okay, you see the intersection, but you don't know exactly where that is. So you got to do some more additional work to get to that value, whether you solve it or use your calculator or you graph it. Okay, but sometimes it's as easy as pulling it directly from what we see in front of us. We just know what to look for. Okay, so we have our bounds, radius, make sure we square our entire radius expression. Quantity squared dy. So I'm looking for the notation, okay? You don't have to show me the calculus steps because the rest is in the calculator, but I do need to see you set up in that form. Now, there's another way that we can rewrite this. This is radical form. Another way I can rewrite this as y over 2 raised to the what?
Oh, 1/3.
Yes, but what if I put everything together?
Parentheses.
Yeah, because I can just put 2/3. Yeah, so it's just an option. If you want to put it as a radical, it may be a little bit cleaner in this form, but I just want to make sure that you understand those are the same things and you can choose. Okay, so I think we're ready to enter into our calculator here. We have everything in place. Okay, 0 to 8. Parentheses. Now, there is a math print option on some of your 83, 84s. So first off, I'm going to do cube root. So math 4 is a cube root option. And you can avoid another set of parentheses if you can get it into this fraction form. So if you do alpha y equals alpha y, some of you may have that option of n over d, being able to get that fraction form to show up. If you don't have this option, then you'll use a set of parentheses instead. But I'm able to get that fraction to show up there. Use x's, don't use y's, x over 2. Okay, so now I'm going to close the parentheses, and then I got to make sure I square it. So look at all those parentheses I got to keep track of. Okay, dx. Okay, did you guys get that? 12.095. If I do math fraction, I don't think it's going to convert. Yeah, so we'll leave it as a decimal. Okay, don't forget pi units cubed. Okay, any questions with part B? Yes.
Will we be counted off if we missed the units cubed?
No, but if a problem is specifying as the unit, then I just want us to get into the habit of understanding that's volume. But if it doesn't specify in the problem to provide the units, then you don't have to provide the units. Okay, but on the AP exam, if it's asking for units, make sure you provide it. Area is squared, volume is units cubed. Okay, any questions? Okay, I want you guys to try part number 2, part A. It's going to feel very similar with number 1A, but I just want us to at least attempt the steps ourselves just to see, are all the steps making sense? Are you able to arrive? If you can arrive at the answer on your own, that should kind of give you just additional confirmation and confidence that you are on the right track and that you're understanding this process. Okay, so try number 2, part A. So you're going to draw your axis of revolution, create your radius. You got to identify based off your radius, do I want to do top minus bottom or do I want to do right minus left? Build your radius expression, find your bounds, either in terms of x or in terms of y, just depending on whichever orientation is given to us. And then also practice entering into your calculator. Okay, so spend some time there. Okay, when you get to the point where you're ready to find the intersection, you have a couple options, right? You can use your calculator, use numsolve, you can graph it, you can use the solver. But if you want to solve it by hand, the hint is that you're going to have to involve natural log, right? That exponent variable is going to eventually need the natural log to help it bring it down. Okay, let's check our work, and I'll go over this problem step by step. So first thing is I saw that my axis of revolution is at y equals 7, so that's where I place my dotted line. I know this is the center of my object after everything gets rotated, so my radius is going to start at the center. So start at the center, I'm going to move in a perpendicular direction to the outer boundaries of my shaded region. And I see I'm dealing with a vertical radius. So vertical radius, I know I'm going to have an easier time because the expressions are already set up for me to build my radius. So the top of the radius is sitting at the horizontal line, which is the 7. The bottom of the radius is sitting at the curve, which is the e to the x plus 2. So then we do top minus bottom. Okay, what do we have to be careful about when you do your radius? Okay, the bottom function requires a what? Parentheses. Yeah, parentheses. So if you don't have parentheses there, you may get caught not distributing the negative through, and some of you may have 9 minus e to the x instead of 5 minus e to the x. All right, so having the parentheses around either your bottom function or your function for your left, if you're doing right minus left, it's going to be good reminders. So in this case, you can leave it in this form. I'm just going to distribute it and clean up so I don't have to deal with another set of parentheses in my problem. So I'm going to say, call it 5 minus e to the x. So there's my radius. Next thing, we still need intersections. If you look, all these vertical rectangles are going to stack from starting at 0 all the way to the intersection. So just like the previous problem, we set the two equations equal to each other. We can also do that here. E to the x plus 2 is equal to 7. I want to solve for e to the x. I want to isolate that e to the x first. So subtract 2 from both sides. And this is where I talked about how e to the x, my variable that I want to solve, is sitting in the exponent region. So I'm going to take the natural log to both sides. Bring the x down. Drop the natural log, and I have x equals natural log of 5. So that's my upper bound, or the bound on the right. Now, if you want to use a decimal value of 1.69, that's fine as well. But I think natural log of 5 is easy enough to plug in where, or 1.609. Okay. I think we're ready. We have our bounds, we have our radius. So we're going to use the first, the top minus bottom formula here. Pi from 0 to natural log of 5. And then make sure that you square your entire radius expression. Okay, so another option that you have in your calculator is, if you don't want to enter everything in the same place, and to avoid the high use of parentheses, you can have this 5 minus, or the 7 minus e to the x plus 2, either form. You can have it stored under your y1. And if you have it stored under y1, then when you're ready to call it, math 9, you can, it's going to look a little cleaner. You don't have to worry about, having to keep track of all the parentheses in the problem. And sometimes if you miss a parentheses, it may either give you the wrong answer or it may give you an error. And sometimes it's hard to troubleshoot those areas, finding where that issue is. So I have it stored under y1. To get to that, you're going to go to vars, scroll over yvars function. And I don't need parentheses here. I can just say squared. And I'll just take everything that I have stored under y1, which is my radius expression, and I can just have a little cleaner expression, and I've done to keep track with all those parentheses. That's part of my problem. Okay, you should get 12.236 after you can either keep that 5, I rounded that 5 to a 6 there, and then pi units cubed. Okay, any questions with part A? Okay. No issues with calculators? All right, let's look at part B. Part B may require a little bit more work here. So, same shader region, same functions, same graph, just a different rotation here. Rotation about the y-axis, that's a vertical line. Axis of revolution is at x equals 0. So let's go ahead and draw that dotted line. Okay, so because our axis is vertical, we know our radius is going to have to be perpendicular to it. So put your pen and pencil on the dotted line first, and now we're going to extend to the right. So we're back to a right minus left form. Our equations have to be rewritten because they are not in the proper form for a right minus left. So I'm going to adjust the equation for the curve. F of x is the same thing as y, so I'll say y is equal to e to the x plus 2. Okay, so I want to solve for x. What would you do first to move towards that goal? Let's subtract 2 from both sides, so y minus 2. E to the x is now isolated, but I want to find a way to bring that x down, so take the what? Natural log. Now, when you take natural log, make sure you have a parentheses around the y minus 2, because that y minus 2 is all going to be inside the natural log expression. The x is now free to move. We can bring that x down from the exponent position, which will make it easier for us to work with. Natural log of each is 1. You can make that drop out. So we have our equation in the proper form. Okay, I'm going to point to it. Left endpoint is sitting on which graph?
Left endpoint is x equals 0.
X equals 0. So again, look at the form we have. They're perfectly set for what we need. X equals, so we know we're in the right spots. Okay, let's build our radius equation, our radius expression. Right minus left, the right endpoint of my radius is sitting on which graph?
ln y
Natural log of y minus 2. Minus, right minus left endpoint is at the 0. We can drop the 0 safely. Okay, let's build our volume and see if we have everything that we need. V equals pi integral. Okay, let's look at the form here. We need y1 to y2. We're stacking these disks from lowest to highest y value. So it's going to be stacked above and below, right? What's the lowest y value that you see? 3. Now, good. We can tell by looking at the graph. Now, if the graph wasn't, or if the y values were not provided, is there another way that we can quickly get to that y value?
We can just set x equals 0.
Yeah, y-intercept is when x is 0. So if you put 0 in for x, you get e to the 0. Anything to the 0 power is 1. 1 plus 2 is 3. So it's another way to find it if it wasn't marked on the graph for us. Okay. What's the highest y value of our shaded region? 7. So it goes to show that there are some times when we don't need to set equations equal. We can look at the graph and just pull it if it's an obvious value. All right, we have our bounds, lowest to highest y value. Now we can work in our radius expression. Make sure that you're squaring your radius. If you don't square your radius, then you're losing that aspect of circle formula that we need, right? Pi r squared. There's that 360 rotation going on. There's going to be a built-in circle for every part of our graph here. So natural log, parentheses, y minus 2, bracket squared dy. All right, let's practice entering this in. Three to 7, parentheses, natural log, x minus 2, parentheses, squared. Okay, 4.857 is what you should have gotten. Don't forget pi, and then units cubed because we're dealing with volume. Okay, any questions so far? Okay, so this is something that we're going to have to be able to distinguish starting tomorrow. But look at where that dotted line is in relation to your shaded region. Do you see how there's no gap at all whatsoever between the dotted line and the shaded region? That's the indication that we're dealing with this method, right? This method. We haven't talked about the other method yet, but tomorrow we're going to see where there's going to be a noticeable gap. Okay, even if there's a sliver of space, even if it's touching or curved region, if there's a sliver of space, we got to use a different method. Only when it's up against a flat surface where you can't see any space at all between the dotted line and shaded region, then you know you're in the right place. You're working with this method. Okay. Okay, so let's finish up with, let's just do part A of number 3. Okay, we'll do part A of number 3, and then we'll be done. Okay, so flip over. So this should be an easy one. Everything should be set up already for you. So let's just finish up with 3A. Okay, let's check our answer here. Your dotted line is going to be horizontal. It's right up against the flat surface of your shaded region. No gaps. This method, top minus bottom, because our radius is vertical. So you start on the axis, because axis is the true center of your object. Extend from your axis to the boundary of your shaded region. We know we got to do top minus bottom. So x cubed plus 2 minus parentheses 2. I like to clean up if possible. Cleans up to be x cubed. So I'm just going to rely on my top minus bottom formula here. I need x1 to x2. I need my left bound to right bound. So I'm going to extend from 0 to 2. Those are my bounds. Radius, make sure you square your radius, otherwise you're going to lose that circle component of your area formula, of your volume formula rather. And then the rest can go in your calculator. If you hit math fraction, it will convert to it'll convert that decimal to a fraction. Don't forget pi. Okay, any questions there? Right. For those of you who've worked ahead, the key is on the website, but you can also check it here. Part B is 3.199 pi. And then number 4 is 0.399 pi and 2 over 7 pi cubic units. Okay, so tomorrow we're going to be taking this concept. If you feel good about this, that's great, because we're just going to extend this slightly tomorrow. Our formula will look a little messier, but you have the foundation to just be able to add a little bit more to this process. But the way that we find bounds, the way that we do orientation of equations are all going to stay the same. We just have to add a little bit more extra to take care of the whole, subtracting out the whole that's going to come out of tomorrow's objects. Okay. All right. Thanks, everyone. Hope you guys have a great day. See you guys tomorrow.